Hello, welcome back, AP Calc. Hey, it's me again. Hey, my program crashed. I think I was asking it to do too much. So let's go back to the graphing calculator for this then. I think it might be a better tool anyway. So over here in y equals, remember we're looking for the answer to this question here is that when is t, or what is t when s of t equals 0? So I went ahead and graphed 1350, and I'm graphing x natural log of x, and I want to see when these things cross. Right away I get, there's your x natural log of x. Looks like a pretty straight exponential function. So what I'm going to do here is I'm going to change my window. I'm not going to really touch x. I know it's probably going to be a positive thing, so I guess I'll go from -5 to maybe 50. We'll see if that works. But for y, I know it needs to be 1350, so I'm going to go from -50 to 1500. And that way 1350 will be near the top, and I'll just use a scale of 100 or so for that. I like to be able to see the x and y axis, so I always set those a little bit later. Looks like I need to go up a little bit more, actually quite a bit more. So for x, let's take x all the way to 1000. I'm just going to guess here. We'll do a scale of 100 for that one. Again, there's 1350, and here's x natural log of x. Much better. There we go. Let's go ahead and use our calculator to find the intersection of that. First curve, second curve, guess, and the answer is 245.333. So this is true at 235 point. I'm going to use 337. I'm going to round properly according to AP Calculus. Let me get my calculator cam out of the way. Although I'm not going to put it too far away because we're going to use it right away. Because to answer this question, what we need to do is take this t value and plug it in for t over here. What we need is v of 235.337. We want to know what the velocity was at that time. So -1 minus the natural log of 235.337, which is going to be a very negative number. Actually, it's not very negative, is it? -1 minus that, it's going to be about -6.461 or so. Yeah, that matches kind of what the book has, I guess. Yes, it's close enough. It's about -6.461, and that would be in meters per second according to the original problem and its units that are in that. Yeah. The published book answer is 6.503. We'll take it. It's an estimation anyway, like that. Now, there's a really good question here, question B. Write an acceleration function for this, and the question is, why isn't the acceleration constant in this situation as it is with dropped objects in the air? Which is kind of a deep physics question, but we're going to answer it anyway. So for part B of this problem, what we need now is the acceleration function, which is the derivative of the velocity function. So we're going to take our velocity function from right here, and we're just going to find that derivative, which is actually really simple. The derivative of -1 is 0, and the derivative of negative natural log of t is just -1 over x, like that. So that is all you really need for that. Or I guess it's -1 over t, if I'm being fair here, -1 over t. And that is meters per second squared. We're being all physicsy about it, being very mathy about it right there. The difference here between air and water, I guess I don't really have a ton of physics knowledge to answer this question. I'm guessing here that water is thicker, or I guess it might be more viscous, might be the word to use. Water is more viscous than air. It's thicker. I guess viscous is like a physics word for thickness. So I guess what the book has written down, which is probably the correct answer, is the friction. So the friction of water, you can't ignore it. It can't be ignored. So I guess water slows things down more than air does. So acceleration due to gravity is not enough. The water affects things. So anyway, let's move on to the next question. 696. We're going to do a little bit of just as kind of theory work here, a little math theory. The integral of x to the nth power for all of these different numbers, 3 through -3. So we're going to do this. We're going to make a little table, I think, off to the side here. This is problem 696. I'm going to grab some space to work with here. We're going to do, we're doing the integral of x to the nth power dx. And for n equals, let's see, I'm just going to think about this. We'll start with -3. So we're looking for the antiderivative of x to the negative third power, like that. So this is basically the reverse power rule. And I guess we really haven't thought about it too much. But if it was x to the negative third power, what our derivative would be, we didn't need x to the negative second power over negative 2 plus c. Because then when you do the power rule here, the negative 2 will come down, multiply in front, it'll fall into that trap, it'll cancel out with the negative 2 and drop down a degree to negative 3. If it was negative 2, you'd have x to the negative first power over negative 1. Again, plus c. The same pattern would happen. The negative 1 comes down, multiplies in front, cancels out with the negative 1, and leaves you with x to the negative second power because it drops down a degree. Negative 1, you might start to see the pattern happening here. This becomes x to the 0 power over negative 1, or sorry, over 0, which is weird because it's kind of undefined. But this is the interesting case, and we'll talk about this in just a moment here. I'll leave it there for now. Then we have 0 and 1 and 2 and 3, and I think you might start to see the pattern developing because it's the same pattern every time. X to the 0 power, well, that would just be 1, so its antiderivative is x. It's x to the first over 1, like that, but that is just x. Again, the thinking here is x to the 0 power is equal to 1. This is just x to the first power, which is x. That becomes x squared over 2. X squared becomes x to the third power over 3, and x to the third power becomes x to the fourth power over 4. And what we're developing here is the general antiderivative for, or the reverse power rule, what's going on here. Now this one here, this is an interesting case. X to the negative first power is equal to 1 over x, and its antiderivative is the natural log of x. So that one's kind of a special case that you need to remember there. It does fall into that pattern, but it takes some mathematics to prove why it does. So that's kind of the special case in this case. However, for generally, a general formula for x to the antiderivative of x to the nth power dx, we call this the reverse power rule. And the reverse power rule is that x to the, the antiderivative of x to the nth dx is equal to x to the n plus 1 over n plus 1. Again, the thinking here is that when you take the derivative, the n plus 1 exponent needs to pop down. It will cancel out now with the n plus 1, and it will drop down a degree to n. And that's the way it works. Plus c, of course. Got to have that in there. And this, of course, if n is not equal to negative 1. That's kind of a special case. We're not going to do problem 97, so let's move on to 98, where we're going to wrap this thing up. 98, calculate the area shown in the diagram between the graphs of x squared, 1 over x squared plus 1, and the x squared. This is technically a non-calculator question, but we're going to do it with a calculator because I think it's going to be kind of silly to do. I think you could recognize for a minute that the antiderivative of this is the tangent inverse. And the antiderivative of x squared is x to the third over 3. But we're going to go ahead and ignore that for now. All we need to do in this problem is figure out what these intersection points are right there and there. And we're just going to set up an integral of the 1 over x squared plus 1 minus x squared. And we're going to let the calculator do all of the work for this problem. So let's figure out what the bounds of this integral are going to be. I suspect they are not nice whole numbers, so let's let the calculator do all of the work for us in this problem. First thing we need to do, let's go back to the basics here. Let's go ahead and graph our general formulas here. We have 1 over x squared plus 1, and then we also have x squared. And for the window, before we push graph, let's kind of mock this window that we got right here. We'll go from -2 to 2. With a scale of 1, and we'll do the same thing for x, -2 to 2 with a scale of 1. I meant y a minute ago. Push graph, we should be able to see a graph looking just like that one develop for us, and we'll let the calculator handle finding the intersection points, and that'll help us set up our integral right there. So again, we'll use the calculator's intersect feature inside of the calculate menu. First curve, second curve. This time, since there are 2 intersections, you do have to put the guess cursor close to where you want it to be. Looks like the first one is -0.786, so I'm going to write that down. And I'm going to go ahead and guess that the other one is positive 0.786, since they are, this graph looks pretty darn symmetric. Yes, correct. Positive 0.786. You could use there's a lot of tricks you can do with even functions like this. You could just do the integral from 0 to 0.786 and then multiply it by 2. That's an option, but we already have this right here. We're going to let the calculator handle everything about this calculation. So we're going to go back out to our main menu. We're going to do the integral fn int. We're going to go from negative 0.786 to positive 0.786, and we're going to go ahead and put our thing in there. It's going to be 1 over x squared plus 1 minus x squared, all dx. We'll let the calculator spit out the answer for that, 1.00856. I like that answer. We'll call it good. And there's no units necessary. I guess you could put units squared on this if you wanted to, since it is an area after all. And finally, let's do a couple of easy derivative. These are fundamental theorem of calculus derivatives, FTC. Whenever you see a derivative with something up there in the top bound, these are easy problems. All we're going to do is take sine of x and plug it in for t, right there. This is 3 to the sine squared of x power. Of course, we then need to multiply. Don't forget the chain rule. The derivative of sine of x is the cosine of x. So we need to multiply by the cosine of x. That's the derivative, and that is the answer. That's all you got to do in this problem. For question B, you might recognize that it's very similar. The first thing I would do in this problem is I would say it's the negative derivative of the integral from 0 to the sine of x of the natural log of t squared plus 1 dt. Don't panic about all this nonsense in here. All you're going to do is take sine of x and plug it in for t. So you're going to have very similar answer for this one. Natural log of the sine squared of x plus 1. There you go. Of course, don't forget to multiply by the cosine of x, which is the derivative of sine of x. And that's all you got to do there, my friends. That's it. Oh, don't forget the negative sign. Negative natural log of t. There you go. All you got to do, my guys. Hey, you guys are doing great. You're killing it. Keep it going. We're going to go as far as we can to the end of the class, and we're going to get there. I think we might just barely get to the end, which is encouraging and cool, and I'm happy to be on this journey with you. You guys are doing great. I'll see you in the next video.